Afternoon, everyone. So I'm the co-founder and the CTO of Terapines Technology. So I bring you the topic accelerate HPC and AI applications with RVV Auto-Vectorization. So because we are a startup, so let me introduce Terapines to you guys. So Terapines was founded by the VP of software of Andes and me at 2019 in Wuhan. So we have 15 plus years of experience in simulation and compiler software. So basically we are a co-design focused company. So we have high performance C++ Fortran compiler, and we have cycle accurate ISR simulator and ESL and the perf profiling tool and the circuit-based RTL simulator. Also, we had the cloud-based IDE C-Studio. So we all know the goods of RISC-V. So we can, it's the basis of vertical computing era. It's free ISR spec and rich software ecosystem. And we can fully utilize the feature to design instruction, customize the instruction, so we can push the upper bound of computing performance in post-more era. So I think the issue we are trying to tackle is how can we do fast software hardware design space exploration. So we need to module the microarchitecture, and we need to iterate the tool chain, the compiler, debugger, simulator in a fast way in order to iterate our microarchitecture. So how can we profile software without hardware available? So also, when we trying to maintain the library and the kernels for various RISC-V-based DSA, how can we optimize the cost to maintain the library and to reach the maximum performance of the library and kernel? So I think, we have, this is a preview of our co-design software. So you can see there's a pipeline level microarchitecture analyzer, and you have code coverage profiler, function level summary. You can see the self-cycle, total cycle in the GUI interface. Also, you can use our GUI interface to add customized instruction. And we have a tool to out-generate all the SDK for your customized instruction. So you don't need to hire compiler, debugger, or simulator employee to tackle all the stuff. All the tools are automatic generated by our IDE. So let me show you some data for our high performance compiler. First, here is the data for SPECInt 2006. So with auto-vectorization, we can achieve 30% dynamic instruction count against LLVM-16. So on RV64 GCBV, it's or not, if you are a compiler guy, who you know it's quite difficult to achieve such huge dynamic instruction count for this kind of benchmark. Also, we have run the actual performance on auto-order CPU platform. So we have achieved 10% better cycle count performance than LLVM-16. Also, we are expecting to have 15% better performance than LLVM-16. Okay, the next slide is the auto-vectorization for AI kernels. So here's the data for various open source compiler, GCC 12.2, LLVM-16, EPI LLVM, and handwritten intrinsic kernels. So the I think it's quite small. So our compiler DSA is at the bottom of the chart. You can see our compiler can achieve roughly 100 times faster than the open source compiler in the warp application. Also, we have achieved 18% faster than hand-optimized intrinsic kernels. So it's quite difficult for compiler to achieve better dynamic instruction count than handwritten intrinsic kernel, because for RVV, the vector length is unknown. So for handwritten kernel, we always can optimize the kernel to specific maximum performance based on the microarchitecture. But for auto-vectorization, as the compiler doesn't know the width of the vector, so it's challenging for compiler to model the cost of the actual hardware. The next slide is the benchmark of MobileNet. So you can see we have benchmarked our compiler against Skinner and against GCC 12.2. So we have achieved 2.5 faster performance against Skinner version. And for vector length is 128. And for if we change the vector length to 512, we achieved 7.7 times faster with auto-vectorization. Also, we have achieved 14.5 times faster than GCC. So this is for MobileNet. And okay, we also benchmarked the famous shift window transformer, which is a transformer-based vision AI network. So you can see for the auto-vectorization, the performance for 128 and 512 vector lengths achieved very good performance against the scalar one. Also, against the GCC, we have achieved 7.5 times faster than GCC. Okay, so all the source code is available from GitHub, and you can ask me to give you evaluating license to reproduce those data. So conclusion, don't maintain hand-optimized kernels and libraries when the compiler can do all the things. So that's our conclusion. Okay, let me show you some example about the RVV auto-vectorization. First, for inner loop auto-vectorization. So the compiler is smart enough to know the induction variable and the actual data which will be stored in the array. So it can combine the extra instructions into the red box one. And for the second example, so our compiler can generate strided memory access pattern for the strided memory access. So this is the second example. And the third example, so we have optimized the cost model in LLVM. So our compiler can eliminate redundant instruction for mixed data type. So you can see we have mixed data type, the char and the int, and we have generated with the ext to minimize the instruction cost for this kind of example. Okay. And next example is for global variables. So because we have enhance the alias analysis path. So our compiler knows if the memory overlaps in the inner loop. So you can see the generated assembly is, the quality is very well. So there's no extra redundant assembly in the inner loop. Next step is the most common optimization in inner loop auto-vectorization. Basically, when the compiler does the inner loop auto-vectorization, it flags all the control flows in the inner loop. So no matter how many if-else in your inner loop, all the base blocks are merged into a single one and be converted into masked execution. So this is the example of flattened if. And also, so our compiler is smart enough to convert math functions directly into RVV instructions, such as square root. Next example is threaded memory nodes. So in this example, the memory access pattern is something that I think is a segmented memory access pattern. So with our analysis path, the compiler can optimize this individual memory nodes into a segmented memory access. So you can see there's VL-seg2, something like the VL-seg2 instruction generated. Those are examples for inner loop auto-vectorization, but there are some drawbacks for inner loop auto-vectorization. Let me show you the example. So, okay, here is the example of inner loop auto-vectorization. So you can see for the innermost loop, we have generated threaded memory nodes for matrix C. You can see the bracket. So, but for many microarchitecture, threaded memory nodes is not optimal. So if we can do outer loop vectorization, actually we can optimize the threaded memory nodes into unithread memory nodes. So if we use pragma to guide our compiler, because it's pretty hard to let the compiler to decide which level of loop should be vectorized. So we use pragma to guide our compiler, to tell the compiler which level of loop should be optimized. So if we auto-vectorize the second level of the loop, you can see all the memory access pattern have been optimized into a unithread memory node, and for the matrix B, it has been optimized into a scalar node. So this is an amazing performance improvement against inner loop optimization. Okay. The next example is a coordination kernel. The left side is a kernel hand optimized by kernel engineers written in RISC-V intrinsic. The right side of the kernel is the C version with pragma, telling the compiler which level of loop should be auto-vectorized. So we can see both kernel both sides of the source code works the same, but so you can see the generated assembly for these two kernels. The left side is generated from the built-in functions. The right side is generated with RVV Auto-Vectorization. Actually, the assembly code is almost identical, and the RVV Auto-Vectorization version is even better with a larger register grouping. So you can see the register grouping is even larger. So, okay. So this is the example for kernels and outer loop optimizations. So the summary. Okay. So RISC-V enables vertical computing era. And we at Terapines, we provide a solution to accelerate software and hardware co-design. Also, our high-performance compiler increased the SPECInt 2006 by up to 10% for scanner, RISC-V scanner CPU. And so our auto-vectorization technology in DSA improves the productivity in library and kernel development. Also, outer loop auto-vectorization can improve the performance against the inner loop auto-vectorization. Okay, and that's all I'm going to share. Thank you.